So welcome everybody to the fourth day of the AGACSE2021 conference in Brno and online. And the first speaker is Anthony Lasenby, who needs no introduction, which makes the life of a chairman very easy. And you'll see the title, Some Recent GA Results in Mathematical Physics. Anthony.
Right. Well, thanks very much to Peter and the other organisers for arranging this meeting. It's really good to be able to see people again after a couple of years. So what I'm going to be talking about today is really in two main sections. The first section will be a continuation of what Joan was talking about yesterday in connection with the rotor which takes one frame to another. And then the second part, I'll move on to some particle physics aspects which I've been working on recently and show how it links with the octonions. I've been interested in the octonions over many years. I really haven't got very far with them until recently. And I finally feel that I do have a handle on the latter entirely within the space-time algebra. And it lends support to the idea I've been pursuing for some while that eventually we'll be able to represent all the symmetries of the fundamental forces entirely within the space-time algebra. No need for extra dimensions or abstract proofs. No.
Roman?
Well, sorry, bring the pointer onto the screen. Bring it first, then see if it advances.
No? If you can advance. No. There you go. Okay, so let's talk about this first topic of the rotor transforming between frames. And in a geometric algebra approach, orthogonal transformations carried out by rotors are which act two-sidedly on general objects in within the algebra by the usual sandwiching R and R reverse. And often you want to determine R given initial and final information about frame of vectors which is being subject to the transformation. And so my notation will be here. The initial frame will be E sub I, and there's a final frame Fi related in this way here. Fi is R, EI, R reverse. And given the EI and the Fi, we want to figure out rotor R. And results for this in 3D Euclidean space and 4D space-time have been known about for many years. See, for example, in these books, I'll be referring to these books, certainly the first one, several times. So I'm going to call Hissner's subject H and S, and the Drone and Lasenby book D plus L. Now, this problem gets rapidly harder as you go up in dimension. And recently, Dmitry Shirokov published a very interesting paper, Calculation of Elements of Spin Groups using the method of averaging in Clifford's geometric algebra in AACA. And this gives a result which, in principle, you can use to find R from knowledge of EI and Fi in any dimension and any signature of metric. And what I'm going to do here, and Joan has shown you some results from this, is going to understand this fully in GA terms and give some generalizations. So talking about what we're going to do that goes beyond the published proof. So the published proof assumes that the EI form a standard orthonormal set. In fact, it should be possible to recover R for any starting set of vectors as long as they span a complete set space. So you can have any non-orthogonal frame to start with and gets rotated to a completely to another frame that is also non-orthogonal. I'm going to clarify that the key result given by Dmitry appears to have a slight difference from what we find here in terms of the order of vectors. I haven't had a chance to discuss this with Dmitry yet. I hope to be able to do that soon. So please regard this as provisional. And finally, the proof given by Dmitry is several pages long, quite detailed, and relies on aspects of matrix algebra that are somewhat extraneous to a pure GA approach. And what I'll be showing you here is a pure GA proof, which can be carried out more quickly and also immediately generalizes to these non-orthonormal frames of vectors. Okay, so we're going to re-examine this result from a purely GA point of view. So in the process of doing this, we're going to find some very interesting connections with some topics in geometric algebra approach to linear algebra, which were pioneered in the book by Hess and Sobczak, but they haven't. We continually find new things in the work that's described in Hess and Sobczak, but they then don't often necessarily get applied in ways that makes us really appreciate what's there. And this will be an application of the subject of characteristic multivectors and their associated use in a GA version of Cayley-Hamilton theorem, which I hope you find interesting. And you'll see that the reformulation of the Shirokov result brings in both these elements in interesting ways, pointing towards yet further generalization. I'm sure we haven't got to the end of this area yet. So the essential objects, and it's introduced by David in the Hess and Sobczak book, are called simplicial derivatives. Jones spoke about this yesterday. This is the case where we've got a function f. It's a vector-valued linear function of a vector a. A is the input, living in some n-dimensional space. And we're going to assume that f of a lives in the same space, this in this case. And we can then define the R simplicial derivative of f as follows. Joe went through this starting from the actual derivatives in terms of the frame vectors. So I'm just going to give you the output answer. And that is that the R simplicial derivative is the partial with respect to the frame of f called sub r, and that f sub r is referring to wedging together our copies. And here's the actual output. It's a sum over repeated indices upstairs, downstairs here, restricted by this ordering, and it's a sum of the reciprocal frame, the reciprocal input frame wedged together here on the left, and the downstairs output frame on the right. Okay, and this is a full geometric product between them. So this is going to have potentially all even elements of the space as output. Okay, and the point about these multivector quantities is that they provide invariant information about the function f. And what do we mean by invariance here? It means that you can choose any frame at all, a sub k, that you like to start things off with, and the objects would still be the same. So that this is the invariance. It's giving us something intrinsic about the space and the function f. Okay, and these are very interesting objects to compute in general because they provide this invariant information. But they haven't been much used. I think I've lost this game. Let's try again. Okay, so these results crop up when you look at the characteristic polynomial and Cayley-Hamilton theorem. But they just use the scalar parts of the various simplicial derivatives. So the scalar parts are scalar invariants, and they're the things that form the coefficients of the characteristic polynomial of the function as shown here. So we say we take the scalar part by indicate that with a star between the derivative and f, and then you sum up some scalar parameter lambda minus lambda to the power of n minus s, and that gives you your characteristic polynomial for the function. And in the normal approach, you would find the roots of that, they'd be eigenvalues of f. And in particular, f of a equals lambda a, these lambdas will be solutions for this equation. And the Cayley-Hamilton theorem is the theorem that a linear function satisfies its own characteristic equation, its own characteristic polynomial. So in particular, you should find that if you take the linear parts of these simplicial derivatives and use them as coefficients in an expansion in powers of f, okay, hope you can see that we're taking f to the power n minus s instead of lambda here. The minus one is got stripped out from just there. So this is the characteristic polynomial evaluated on f, and that should give 0 at any input vector a. Okay, so what we're going to do, this is a start now of, that was general. We're going to start now on a result for reconstructing a rotor. And what we're going to do is let f be a rotor. So f of a is RA R reverse, where R reverse is 1. Okay, so that's our function for a general vector R. And we're going to supposed to start with that the set A sub I from I 1 to n, form an n-dimensional frame. Sorry, what we're going to start with is, I shouldn't have said that. We're going to start with an orthonormal frame when we're doing the proof, and then I'll generalize it to a general frame. Okay, so the input eventually will be a completely general non-orthogonal frame of this form, and the output will be always Bi is f of Ai, which is then Rai R reverse. And I'm claiming that will work for any input frame. So our basic claim is that the reverse of the rotor is a scalar multiple of the sum of the characteristic multivectors of f. And so in particular, R reverse is the scalar multiplier alpha times the sum from R equals 0 to n of these characteristic multivectors. It's a really nice and simple formula. And of course, the dr, fr are given by the input and output frames by equation 1. And this is meant to apply in any dimension and signature. So how does this work? This is where we do drop down, first of all, to the case where the frames are orthonormal. And so we now write AI is some EI, where this is an orthonormal frame. And then let's do the sum on the right-hand side of 2. I'll attempt to go back to 2. Okay, so this is the sum we're interested in. And we need to take the different simplicial derivatives and sum from R equals 0 to n. And so this is straightforward. We form the reciprocal frame to the A's. That's just these upstairs things here. We have them in the reverse order. So it goes from EJR down to EJ1. And then we sum those with R, EJ1 reverse, R EJ2, R reverse, etc. Now, because these are orthonormal, well, actually, no, sorry, quite generally, R reverse R is 1, of course. So we can strike that out. The whole thing here is just the R, EJ1, EJ2 through to EJR, R reverse. And so we can write that. Let's pull this R reverse out to the end. We can write that as the sum from R equals 0 to n of the EJR through to EJ1 upstairs, sandwiching the rotor R, EJ1, EJ2 through to EJR downstairs. So this is looking promising. We'll have proved the result we want if we can show that the double sum within the brackets, it's double because these J's are summed over, is just a scalar. If this is just a scalar, this will give us the alpha that we want. So why is that true? Well, if we divide the overall 2 to the n dimensional space into vectors, A, bivectors B, trivectors T, quadrivectors Q, and so on, up to some Qn, say, where n is the dimension of space, it's easy to see that this quantity written down is in fact this thing here. We've got R from the scalar bit, dA, Ra from the vector bit, etc. We are taking derivatives which sandwich the thing in the middle in this way. We're just summing over all the possibilities that we could have. And at this stage, it's clear that the rotor nature of R is irrelevant, and we're in fact seeking to show that M plus dA, MA, etc. is a scalar for any general even element M. Now, why is that true? We can make this easier by recognizing that what we're now doing is forming a derivative with respect to all the 2 to the n independent elements in the space. Let's write those symbolically as EJ, J plus 1 to big N. And what we want to show is that in the usual multivector derivative notation, if we differentiate with respect to the general element E through M, we get a scalar for any even element M. So write that again, dE, R part of M, E equals 0 for each even grade R greater than 0 in the space. And we can rewrite that like this. It's basically going to be the sum from 1 to 2 to the n of E upstairs J reciprocal frame M EJ. So what we want will follow that each even basis element of the space, apart from the scalar identity, commutes with n over 2 elements and anticommutes with n over 2, because then everything will cancel out in pairs. Okay. Is that true? That's exactly what we would expect. This is just saying the thing about if we're cancelling out in pairs, all we get left with is a scalar, and so we know that DEME is 2 to the n times the scalar part of n. And that is exactly right as regards the commutation, anti-combination properties for the full set of elements. Think about each element being made of a given number of mutually anti-commuting vectors, and then you pass through these elements E, and you count how many times they flip sign. And you'll find that everything cancels out except for the scalar part. So that's that. And everything we said would apply actually completely equally to the case where the A's are non-orthogonal. All you need to be able to do is form reciprocal frames. So that's the limitation in the proof. We need cases in terms of dimension and signature where you can always form reciprocal frames. If you can do that, you're done. And this works. Now, I said it always works. There's one catch. And you can see an important special case will arise, and the above method will fail to return a rotor if it happens that the rotor we're trying to recover has a zero scalar part. Because then the sum of the characteristic bivectors will just return 0, because that sum of characteristic bivectors is returning the scalar part of the rotor. And if that's 0, then you've got a problem. So there's nothing wrong with the mathematics in this case. It's just that the factor in front of the R reverse, which we now know is 2 to the n scalar part of R, will be 0. And does this happen? Well, quite a lot. An example of a rotor with 0 scalar part, you can consider 180 degree spatial rotations. So in ordinary Euclidean space, R equals E1, E2, rotates both the E1 and E2 axes by 180 degrees. It leaves the other axes alone. It's just a bivector, no scalar part. And it's also possible to have rotors with neither a scalar nor a bivector part. For example, in 4D Euclidean space, then the pseudoscalar E1, E2, E3, E4, you might not think of it as a rotor, but it is, because it satisfies I/R reverse equals 1. Okay, so what does it do? In what way is it a rotor? That rotates all 4 axes by 180 degrees. Okay, now, in the paper that Joan and I are writing on this, we extend the algorithm to include these cases. And actually, it's quite simple and doesn't require much extra work. You can see what happens in this case where it's just a bivector. You flip 2 axes by 180 degrees. In the case where you've got a full pseudoscalar as the rotor, but nothing else, then it's rotating all 4 axes by 180 degrees. If you take out those rotations at the beginning, then decompose, well, add up the characteristic multivectors to get the rotor, then it will give you something with a non-zero scalar part from which you can recover the rotor, and then you can flip back by using these rotations. But these are the simplest forms of rotations because they're just sign flips. And so you don't need any extra work really, other than evaluating the sums gain with certain combinations of the outputs Bj split and sign, okay, which is quite an easy thing to do. So basically you can do this and recover the correct rotor without knowing what the correct rotor is beforehand, which is an important point, and the procedure is properly algorithmic, and provided the true rotor is non-zero, the method is guaranteed to work. There must be some grade eventually which is returning non-zero, and so you know that the method will work eventually. So the details for this will come in the paper. Now, how does this compare with the Shirokov results? He gives his main result in his equation 6.1, and translating it somewhat, this is if 2 orthonormal frames, EA and beta A, are related by a rotor S, as shown just here, then if you write M is 1 plus beta A EA plus something that we'll just look at in a second, beta 1 to n, e to 1 to the n is non-zero, then S is given by this multivector divided by the square root of m reverse n. Now, this notation with the betas 1 up to k is explained in equation 2.4, and basically it is this product beta a1 up to beta ak over this ordered set of indices. And then we look at the reverse of the right-hand side of our equation 3, and we can compare with our result for the orthonormal case, and it would be this. So it's the sum of beta j1 through jr reverse, bj1 through ejr. If I can go back, you can see that the beta that he's using is actually the reverse of ours. Okay, I don't know how clear that was, but I just go back again. You can see that just here, the betas go up in ascending order, just here, and that is the opposite of what we're finding. So our beta factor is the reverse of Shirikov's, and this will cause a sign difference for each r, such that when you reverse the E1 through ER, you get minus what you started with. Now, actually, that happens in 3D, which is the example of using the formula that Dmitry Shirokov gives. And so if our ordering is right, then Shirikov's formula will give different results even in 3D. And indeed, if you check this, you find that for orthonormal bases in Euclidean 3-space, the result from Dmitry Shirokov always returns 0. Whereas as long as the scalar part of the rotor doesn't vanish, we recover the intended rotor. And the reason that his result vanishes is that because with the ordering of factors given in this paper, the bivector part of the sum in our terms cancels the vector part, and the trivector cancels the scalar part. So I think one can see from that that there is a problem. With our signs, they actually reinforce each other, and you get the expected formula. R goes like 1 plus beta A here. Now, I'll seek to iron this out with Dmitry soon, but it looks as though one needs to flip the order of the vectors. And of course, what we're doing here extends to non-orthogonal frames. And also we've discovered that there's actually important, genuine cases where it returns 0 and where you need to be careful that there's an algorithm to get around that. So that's given the proof. It probably took me longer than it should have done. If you actually have a look at the proof in terms of what you're doing, you can see you're just doing that derivative d sub e, object e, and that strips out everything except the scalar part. And basically, if you're happy with that, the proof is just a few lines long. Okay, so I just wanted to give an example of why this sort of thing is interesting. Joan has already talked about this. I'm only showing this particular thing for the reason that I showed this first back at a meeting, the Grovisma meeting in Pilsen in the Czech Republic back in 2009. So this slide is from there. And this is just showing what happens for a particular version of the hard transform. So here we have the basis states for a hard transform. We're going from, I define it like this, an E1, E2, E3, E4, which you can think of as an orthonormal pixel basis, to this set of functions here. The first one's just the scaling function, so everything's plus, and then here the F2 through F4 are relating to these patterns. Now, these are orthonormal, so there's a rotor taking one set to another, and here is the rotor using the above method. It's nice and simple, and you can then apply this recursively in a double-sided fashion to an image in order to carry out the 2D hard transform. And I just thought you might like to see some quite surprising properties of this R. In particular, you find R squared is minus R reverse, and that in turn means that R is a 6th root of unity. so r to the 6 is 1. Now, given a rotor, we can of course interpolate, and that's what Joan was talking about, and thinking about it here in terms of an e to the b form of transformation rather than the fractional Cayley transform Joan was using. Let's see if we can get the interpolated Haar transform for the using the exponential form, and the logarithm of the transformation is very simple. The rotor is the exponential of the following blade. You can just factorize it out, and here's the explicit blade you take e to the b of to get the Haar transform. This squares to -3, and the general interpolated rotor is r of alpha is cos alpha plus 1/√3 sine alpha b. And the actual Haar transform then is where you have alpha is pi/3, but then you have all these other possible transforms for different values of alpha. So this example was, as I say, in my talk in 2009, and one of the things I wanted to do following this was move on to more ambitious rotor decompositions in many more dimensions for attempting possibly fractional rotor versions of things like spherical transforms. At the time, I was particularly interested in spherical transforms from the point of view of analyzing the microwave background around the sky. It's something that is very important numerically to be able to get fast versions of spherical harmonic transforms. And so what I was attempting to do was find a rotor version of spherical harmonic transforms, which you could then split, find the logarithm of the rotor, split it up into commuting bivectors, and then when you exponentiate, you've got something where you can do all the individual ones very quickly because they're just simple exponentials. You can just write down cos and sine and so on. And then you'd be able to perhaps have a fast version of the spherical harmonic transform, which would be extremely valuable. And it all depends upon this decomposition into commuting bivectors. But back then, I think I got about as far as about 12 to 15 in terms of the dimension of the space I was working with. Then it got much harder. Now, and also I wasn't working systematically on this. Now, I think this is a very good time to go back to that sort of endeavor, given this recent paper from Martin Reltz and Stephen DeKennick. You heard something about it yesterday, and Martin will tell us more later. The paper is Graded Symmetry Groups, plain and simple, and this systematizes the decomposition of rotors and bivectors in a way which makes explicit in higher dimensions methods which were already sketched out in Hessler's object, but this makes it much more systematic and gives explicit solutions. If you've got the lambdas in the eigenvalue equations, it tells you how to get these parts of the bivectors. And so what I'm going to do now is I'm going to draw a connection between this issue and characteristic multivectors. Characteristic multivectors were key to getting the rotor from one frame to another. We assume we got our rotor, we want to split it up. So the next thing is there a role for characteristic multivectors in this splitting up? And we're going to be looking at that in the context of SU3. I've stimulated to this partly by stuff I was doing with SU3, with a completely different context. I'll talk about that in a minute. But Martin began looking at SU3, coming out of his particle physics work in a geometric algebra approach in his thesis. And he's translated some of that into conventional matrix approach in this paper here. And that leads to a decomposition of a general bivector generator B of SU3 into 3 commuting bivectors. And what I want to show here is how the characteristic polynomial necessary to do this split arises in the characteristic multivector approach that we're pursuing here. Okay, so this is what my approach is. Shouldn't say my approach. This is the approach I'm going to talk about for a bit, of how you can use the Cayley-Hamilton theorem and characteristic multivectors in looking at a finite rotation. Sorry, we've already done the finite rotation. A equals f of A equals R reverse. We want to look at the generators of finite rotations, which is how people think about things like SU3. They think of it as a Lie group, so they want the generators. And that's what we're looking at here. So if you drop down from R reverse as being your output to f of A is just B dot A, where B is the bivector related to R by R equals e to the minus B over 2, then you're looking at the basically the Lie group representation. And what we're going to show is that the characteristic polynomial indicating Hamilton theory for this UF is precisely the polynomial we need to use for the process of splitting B into commuting eigenblades. And this is recognized on page 82 of Heston's subject, and there's a way of thinking about what has been done in a new paper by Martin and Stephen. So we're going to be looking at this for SU3, and the approach which we both use in this context is this Lie groups and spin groups approach of Chris Brown, David, and others. And this is a way to work with all unitary groups in terms of geometric algebra of dimension twice the dimension of the space. So SU3 is a 6-dimensional space. You end up with 6-dimensional algebra in which the action of a bivector generator is just as A dot B or B dot A we talked about. Now, for the special unitary group, the way this works is that the bivector B is not the most general possible within the 6D algebra. If you think about how many bivectors you've got in a 6-dimensional algebra, you've got 15. But there are, in fact, only 8 generators of the group. So what's going on there? The correct generators are picked out by commuting with J, the effective imaginary for the space, which if our 6 basis bivectors are E1 through E3, F1 through F3, all mutually orthogonal, so they anticommute and square into 1, then the effective imaginary for the space in this approach is this. J is E1 F1 plus E2 F2 plus E3 F3. And if you look at all the possibilities for bivectors which commute with that J, you find these are the possibilities. So you find that there's a set Eij, big Eij, which work like this, Eij plus Fi, Fj, I less than J. Then you get some Fs, which work like this. You have EF, EF combinations. And then you get sort of partial bits, the things that make up the big J we just talked about. Ji is Ei, Fi, but there's no sum on that I. And so this brings it down to 9 possible objects. Okay. Now, for the special unitary group, you've got one more condition, and that turns out to be the condition. This is where you want the determinant to be 1, basically. It turns out you need B dot J equals 0, and that defines a special unitary group. And for this, the generator matrices, we go back to matrices of traces. Okay, what does B dot J equals 0 do for you? It turns out it means that the combinations alpha 1 J1 plus alpha 2 J2 plus alpha 3 J3 have to satisfy alpha 1 plus alpha 2 plus alpha 3 equals 0. It's quite easy to work out that's a requirement. So then you're down to 8 generators, and those are the equivalents of the 8 Gell-Mann matrices in particle physics. Now, this is all well understood from the perspective of the Lie groups and spin groups paper, and we included quite a bit about this in the Duran and Lasenby book. Now, what I'm going to talk about now, though, goes a bit beyond this. I want to give some specific details for SU3, which go beyond the details presented in those, and show how it links to characteristic multivectors. So we can write down specifically the analogues of the Gell-Mann SU3 matrices like this. So it turns out that the Gell-Mann lambda 2 matrix is a half E1, 2, lambda 5, half E1, 3, and 1, 4, and 6 are the Fs, and 3-legged combinations of the j's. And I've used equal signs here. The things on the left in this setup are still geometric algebra quantities, but the important point is that, for example, if you took their commutators, they satisfy the same algebra as the SU3 normal generators and the lambdas, which would be the matrices. And this leads to some quite interesting things. So the anti-commutators immediately give you the structure coefficients for the group. They work out immediately. But you can do further things like this. Because they're GA quantities, you get some quite interesting geometric structural relations. I find this one quite an interesting one. I'd never known much before doing this about the so-called symmetric structure constants for groups. Just being familiar with the antisymmetric ones, it turns out if you take lambda I times wedge lambda j, which is therefore a grade 4 thing, you dualize it with the pseudoscalar for the whole space, and that brings it back to being a bivector. You find that's 1/6 delta ij times this imaginary minus dijk lambda k, where this dijk is completely symmetric. And they're known as the symmetric structure constants of SU3, or any algebra of this type. And you can see how duality works here to bring the exterior product of the lambdas back to a representation in terms of bivectors. Okay, so what I want to talk about now, though, is how about the characteristic multivectors and the Cayley-Hamilton theorem for this case? So with f of a equals b dot a, where b is a generator bivector in SU3, we can now work out explicitly what the characteristic multivectors are. And I've gone through them here. So the first one is going to have to be something that makes sense, is sort of intrinsic to the space, and it returns -2 times the bivector. So that's fine. It just returned the bivector. And the scalar part of this object, which would be the trace in the conventional matrix approach, is of course 0. So that fits in. For the next one, so this is, we're aiming to get to D2F2. And to get to that, I'm going to define some coefficients. I'm going to express B as Bi lambda I, where the I is summed over 1 to 8. And so we're expressing in terms of the equivalence of the Gell-Mann matrices. And we'll say the length of B is Bi, Bi. So if you do that, the second one is this thing here. It's grade 4 bit B wedge B and a scalar bit half B squared. So they both look very sensible. The next one, the third one, introduced just last bit of notation. And it turns out this introduces the determinant of the transformation already at this third stage. And the determinant I'm going to talk about is this. If I let's use big lambda to be the actual Gell-Mann matrices, and let's form in matrix terms the general generators. I've added together with arbitrary coefficients all 8 ordinary Gell-Mann matrices. We get a matrix M, which is given by this. And the determinant of this matrix M is real. So we're quite lucky. It means we can use it without having to worry about incorporating a scalar imaginary, which I call as a J here, into our 6D formalism. And what you find is that for R equals 3, you find the third multivector is this thing here. It's got grades 2 and 6. Then we get a bit here that's just multiplies B. And then there's a J plus 4I det M. And that, again, looks very nicely intrinsic and invariant in the space. And we carry on. I won't go through all these. We get a fourth one, the fifth one, and then for R equals 6 is quite interesting because we get D6F6 is 1/64 det squared M, I grade 0 only. And it's interesting that this top level characteristic multivector, which would normally return the determinant of the transformation, here returns the determinant squared, and we'll shortly understand why that's the case. So let's look at these results in terms of the characteristic polynomial and Cayley-Hamilton theorem. that just uses the scalar parts of these things we found. And we've said what the characteristic polynomial is. It's this thing involving sums of the scalar parts. Let's work it out. We find out characteristic polynomial is then this thing here, 1/64 det squared, 1/16 mod b to the fourth times the lambda squared, and 1/2 mod b squared lambda to the fourth plus lambda to the sixth. And so for the Cayley-Hamilton theorem, we would substitute f into that, because the Cayley-Hamilton theorem is this thing that the function satisfies its own characteristic polynomial. What does that give? That tells you that the f should satisfy 1/64 det squared m a. That occurs because f to the naught of a, f of a is b dot a, remember, in this. You've got 1/16 mod b to the fourth f squared, 1/2 mod b squared f to the fourth, and then an f to the sixth. And just to say that for a completely general SU3 element, you can explicitly evaluate this equation, this one at the top, and you find that the left-hand side vanishes, and so the Cayley-Hamilton theorem is indeed satisfied. But now at this point, we can start comparing with treatment given by Martin in his geometric invariant decomposition paper, and he's finding the decomposition of a general SU3 element into traceless skew Hermitian matrix B, which is represented by that, into three commuting matrices B sub I. And the key equation in that for getting these eigenvalues is as shown in the top thing here. This is in matrix terms. And from this equation, which now, note, just goes up to lambda cubed, you can find three roots, which will all satisfy bi squared equals lambda I, and you can do the decomposition from that. If you compare with the equation we've got here, which we just found for the characteristic polynomial, it's obvious what's going on. We can see it clearly here. Let's go back to this equation in f. Only f squared, f fourth, and f to the sixth enter this. You only get the square of the function a dot b appearing, and this is because if you have your f of a equals a dot b, the Cayley-Hamilton theorem applied to that yields an equation for the eigenvalues of the symmetric function f squared. And this is in Hessianism's object, but I'd never taken it in and understood how it related to this until doing this work. And basically, if you work it out, if your f is a dot b, f squared of a is a dot b, and that is a symmetric function. You can see it's symmetric because its curl vanishes. If you take dA of f squared of a, that's dA of a dot b, that works out to minus mod b squared. So in fact, its curl vanishes, therefore it has to be symmetric as a linear function. And so what Martin and Stephen are doing is re-expressible back in this case as a Cayley-Hamilton theorem for a function f equals a dot b, which by itself yields this f squared function, which is purely symmetric, and then you, of course, you get the eigenvalues because it's purely symmetric, which is quite nice. Okay, so it says the same thing here. The characteristic polynomial for f of a equals a dot b yields a polynomial in the squares of our lambda quantities, and these are the coefficients needed in the decomposition to find out to be. So there's more to do on this, and in particular, I haven't really tied this through properly to the business that the rotor is the sum of the characteristic multivectors, but the various pieces in the overall sort of puzzle are getting clearer, I think. Okay, so I think I now move on to the next part of the talk. Okay, so there's a bit of a change here, but SU3 will come through still as the one of the main items. So, forces of nature, what are they? Well, we know there's electromagnetism, weak interaction, strong interaction, and gravitation. And if you've watched my talk at the Game 2020 meeting, then you'll know that I'm particularly interested in whether the space-time algebra, which is just four-dimensional, is the algebra about the space we actually sort of know is there, is sufficient for representing, deriving all the forces of nature. Now, electromagnetism and gravity fit extremely well in the STA context. On the gravity side, I could refer you to the gravity gauge theories and geometric algebra paper published back in 1998, which shows how beautifully geometric algebra and gravity's gauge theory fit together. What about electroweak and strong forces, however? Well, for electroweak forces, various people, David himself, Chris, myself, and Anthony Lewis, who was a student of ours, they pointed out that given an STA Dirac spinor psi, and for the electroweak case, that will be some combination of massless left-handed electron and neutrino wave functions. Then starting from a Lagrangian, you find that the symmetry you should be looking for is to find all multivectors n, such that when psi is multiplied on the right by e to the n, then psi gamma naught psi reverse, which is the Dirac current, is invariant. Okay, just to emphasize, this is all in the ordinary space-time algebra. We're going to electroweak, and we know we're doing that because we're looking at things on the right of the wave function. And if you ask that the Dirac current is invariant, it picks out a set of bivectors which obviously have to do with gamma naught, and that's I sigma 1, I sigma 2, I sigma 3. It also happens to pick out the pseudoscalar. If you have e to the beta I, then although it doesn't, when it reverses, it doesn't change. As the I goes through the gamma naught, then it flips and you get something which is a symmetry. And so you end up with the I sigma 1, I sigma 2, I sigma 3, and the pseudoscalar I as the possibilities. And so the I sigma I bits thus form a spatial rotor R, which defines the SU2 part of the electroweak transformations, and the action pseudoscalar is just like a phase rotation, so it's U1. So straight out of that, you get an SU2 cross U1 gauge group of electroweak arising naturally from symmetries within the STA. Then, as you carry on to do more within the STA approach to electroweak, you find that mass can be generated by interaction with the Higgs scalar, except I put scalar in quotes because it turns out in this approach that it turns out to be a Pauli spinor rather than actual scalar. Then you think, well, why do people think of the Higgs as a scalar particle? It's because the scalar aspect arises from the fact it doesn't transform under Lorentz transformations at the left of the wave function, only electroweak transformations at the right. And that's what the Higgs particle is in this approach. It's a Pauli spinor, but only transformed on the right. So electroweak fits in fine with the STA program, although certainly some details remain to be worked out. And in the form just described, it doesn't really shed light on this basic question: why does the SU2 symmetry only seem to be employed for left-handed wave functions? We were talking about this with Gene the other day with his talk. So that's electroweak. How about strong forces? And we know that the group we want here is SU3, but the mathematics of SU3, as we were discussing it just now, either in my approach or Martin Rolf's version, is set in a 6D Euclidean space, in which we're employing this Lie groups spin groups approach in order to represent the action unitary groups smaller n in the space 4 to 2a. So you've immediately that stepped outside 4D space-time. So there's two developments relative to this which I want to talk about. The first is something I discussed in Game 2020. So if you have watched that, then some slides coming up will look familiar from that. And secondly, linked, it's becoming clear to me that octonions may hold the overall key. As I said before, I found out how to represent them using just the STA, and how their key feature of preserving the norm of elements under multiplication fits in with both the electroweak and strong force STA approaches in a rather interesting way. Okay, so this is the GAIN 2020 bit. So how would we like to represent the strong force in the STA? And there's a model initially due to our son, Robert Lasenby, which I think is the key to this. It extends the Dirac spinor psi to be both a function of position x and a linear function of a bivector argument b, so that psi is psi of b, as well as having a position dependence. The separate color fields then arise like this. You think about the action of psi on bivectors, and these bivectors, sigma I, are just gamma I, gamma naught, I equals 1, 2, 3, in the usual way. And of course, this thing of having a spinor as a function of an input bivector, here the sigma I, and position is intriguingly like a sort of spinor version of the Riemann tensor. This Riemann tensor takes an input bivector, spits out an output bivector, and is a function of position. Here we're spitting out not a bivector, but a Dirac spinor. And recently I've made a definite proposal for the form of these transformations of B, which gives a nice picture within the STA of the particle physics version of the SU3 group. And this is that we ask for transformations of bivectors F in the STA keep the Hermitian inner product of F with itself invariant. And this is the Hermitian inner product of F with itself. It's the scalar part of gamma naught F, gamma naught F. And why is that? Hermitian adjoint is reversion followed by reflection of the time axis. If you revert a bivector, you just get minus a bivector. So going back to here, we've got, conceptually, you can think of this as F reverse in the middle. So you've got gamma naught, F reverse, gamma naught times F. That's the Hermitian inner product. And what are the operations we carry out on this? We do this by considering double-sided operation on F. And again, must mention that David had got certainly part of the way to this several years ago. The first thing that I know about where there's proposed to be a double-sided action to understand SU3 was in this paper here, towards the end of this paper, Space-Time Structure of Weak and Electromagnetic Interactions, Foundations of Physics, back in 1982. Okay, so, but what happens here is systematizing the whole thing and making clear how it works in the context of the type of generators that we had before for UF in the Lie groups and spin groups approach. So again, we have a little e and a little f, and now these are operators. I mean, ei as an operator is multiplication on the left by sigma I, there it is. F as an operator is multiplication on the right by I sigma I, there it is. And quite unlike what happens in Lie groups and spin groups, these EIs and FJs, they commute, right? In the Lie groups and spin groups approach, all the vectors from the different spaces anti-commute. Here, everything is commuting. So it's really surprising that this works, but it does. So we then define the same sort of thing as before, an EIJ, which is an EEFF, and a big F, which is an EFEF, and then the J's again. And it all starts going through the same way as in Lie groups or spin groups, but now this is all just in the STA. And in particular, the restriction from U3 down to SU3 happens the same way as before. If you look at the sum of the J's, and just look at what a J is, a single J is exactly the same as before. It's an EIFI with no sum on the I. And the sum of them is, again, this thing that called big J. And if you work out what it is, big J on F is minus IF. So that's very nice, the J here acts like a generator of a global phase rotation, but where the imaginary is a pseudoscalar of 4D space-time, which makes a great deal of sense. And it's this pass you've got to remove by making the transition to SU3, and that ends up with the same criteria. You've got to remove combinations to form alpha1, J1 hat, alpha2, J2 hat, plus alpha3, J3 hat, where alpha1 plus alpha2 plus alpha3 equals 0. That's the condition you need, and that limits you to 8 instead of 9 generators. I won't spend long on this, but in this approach, it turns out you don't need to bother with decomposing into commuting bivectors. Well, first of all, these are operators, not bivectors, but they're already decomposable immediately. You can take the exponential straight away to find finite forms of the transformations. So, for example, if you look at the two individual parts of the EIJ generators, which is little e1, I, little ej, and little f, I, little fj, it's clear they mutually commute, and each squares to -1. And so you can write down immediately that if you exponentiate the EI, the finite transformation you obtain is this rather nice rotor here. Rij is a spatial rotor, alpha over 2, sigma I, sigma j, and it just rotates your input f. So if R is a general spatial rotor, has 3 degrees of freedom, we can now see that the E sector amounts to the set of spatial rotations R at R reverse. So we've uncovered very nice symmetry beneath what happens with the big E's.
We're approaching the end of time.
There's a bit more to go. For the F's, you expand those and you get this not quite so pleasant form here, but it's very quick to get there because, again, you can exponentiate the individual parts. And to complete the set, the finite form for Ji is shown just here, exactly what you'd expect, given its what it is duality. So the J itself is just a duality transformation. Okay, so this all looks quite promising, but I'm confident it can be done with wholly STA entities. But of course, you're still only dealing with one generation of particles. And of course, we know there are actually not 3 factorial, but there are 3 generations of particles we need to deal with. So what do we need to do to enlarge the opportunities for representing particles while still staying in the STA? And the clue for me has come from what Cole Fury, some of you will know her, she spoke at the ICCA in 2014, I think. And over the last few years, she's been using octonions coupled with Clifford algebras in a way which expands greatly the opportunities for representing symmetries. And here's a representative paper from 2015. She was approaching octonions initially outside of Clifford algebra, but more recently has been making the link with spaces like CL60 and what you heard about from G the other day. Now, in fact, even these in general not big enough to encompass all the particles and interactions we want, but Cole has been using a very clever technique to do sequences of octonions to pack in a great deal of information, despite the relatively small size of the spaces involved. Now, I'm not going to be able to go into any detail about the properties of octonions, but you'll all know that they're non-associative, okay? There's 8 of them, and they're all, the product is non-associative. So in particular, if I've got some state phi, I act on it with an octonion B, then I act on it with A, I have to keep this bracket in place here. I can't write that as being the same as AB with a bracket around that acting on phi. The product is non-associative. And why is this interesting? Is because you can store up an awful lot of information by forming sequences of multiplications to either the left or right of the object. The lack of associativity means that you get a lot more information encoded in that. It is something like a code, than you could ever have for an associative product. And the possibilities obviously increase greatly as you go to long sequences. And what I found recently is how to represent octonions and the states they operate on entirely within the STA. And the octonions become direct spinners, which are 8-dimensional space. And for each spinner, we need to find the parts that commute or anticommute with gamma naught. Either basically, we're talking about their Pauli or non-Pauli parts. And if psi, the direct spinner, is being thought of as an octonion, we define psi plus is this part where psi that commutes with gamma naught, and then another part psi minus that anticommutes with gamma naught. And then given two octonions, phi and psi, their product, and I'll denote it with this sort of star thing, it is the direct spinner theta given like this. So the output's a direct spinner, we take psi star phi, and that's this sum of 4 geometric algebra STA products. Psi plus, phi minus reverse, psi minus. Well, you can read the rest for yourself. It's quite complicated, but there are just 4 of them. And of course, you can work these out very simply. You've got any program which can do 1 and 3 space. Now, from the form of this, you can see that such a product is highly unlikely to be associative. And in general, of course, it is not. And in fact, this gives you a perfect mapping. Of course, you have to assign the direct spinner elements to octonions, but it gives you a perfect mapping for the octonionic product. Now, although such a product is not associative, the property it does have comes from the essentially defining property of the octonions, that they form a normed division algebra. So to get ourselves a norm, you need to define a conjugate element. And for us, we use this asterisk type thing to denote conjugation. So it turns out that psi conjugated in an octonionic sense is psi plus reverse minus psi minus. And that yields the following norm. And this is the bit, right? This is the bit I found really surprising and is extremely interesting. The norm is mod of psi, normal psi, which is psi octonionic product with the conjugate thing. You work it out, and it comes to this j dot gamma naught, where j is the direct current. So the norm here is the time-like part of the direct current. And of course, we know from its interpretation's probability current, this is why it works so well, that j is always non-zero at future pointing as long as psi is non-zero. So it can function perfectly as a norm. And of course, it's a scalar in the sense that the grade is present, so it coincides perfectly with all the properties a norm should have. Now, what you need for an octonionic norm is, and for this to represent a norm division algebra, is the fundamental relation that the norm respects multiplication. So we require that psi star phi should be psi mod phi. This is this crucial relation that I was talking about on Tuesday, that the norm of the product is the product of the norms. Does this work? And it does. And basically, you can work out that this happens perfectly, and you're taking the product of the time-like parts of the direct current. So I'm close to the end now.
Indeed.
So the fact that we get that happening sets this approach apart from trying to do things just for the ordinary Clifford product in either the STA or CL4, for example. The states 1 plus sigma 3 and 1 minus sigma 3 provide a counterexample of the STA. And in the talk Tuesday, I was drawing attention to a half 1 plus I, half 1 minus I. They stop this working if you try to do it with the ordinary Clifford product in CL40. Now, excitingly, we can start to reinterpret what we've already discussed above the STA approach to the strong force as a partial piece of a grander project for understanding the symmetry that nature wants us to use. So here's a proposal, right? You've heard it here first. Nature is interested in transformations that preserve the time-like part of the STA direct current. Okay, and this is going to be instantiated by using octonionic multiplication to represent operations upon states, since this can preserve octonionic norms, and we've just found out they're actually the same thing as the time part of the direct current. And this is palpably what we've already done so far, the two things I've already talked about, as giving you symmetries that we want within the STA. In particular, for the electroweak case, we actually went sort of one further. We didn't just preserve the time bit, we preserved the whole direct current, and that gave us SU2 cross U1. So that's fine, but we were certainly doing this thing I've just said. For the strong force, we were preserving gamma naught F, and that is precisely the same as using not the whole direct spinor psi, but just using the bivector part in forming the direct current. So what we were doing there was the direct current, but for a special type of psi that was just itself a bivector. So in fact, I haven't had a chance to go back and understanding it. This is a proof that I must have been doing octonionic multiplication in this STA version of SU3. There's no way around it besides preserving the norm that is part of the direct current. So it'll be very interesting to go back and understand what I was doing there. And then finally, I've done a great deal more on this. Things seem to be hanging together well. It has a good time with work by Colfury, Dixon, Gray, etc. But here it's instantiated with just the STA, which I think it will help define the structures better since it's more restrictive. And so finish with watch this space.
Watch this space time.
Yes.
Are there any?
Yeah, I think the idea of...
Oh, sorry, you need the microphone.
You will need to turn it on.
Yeah, I just...
I think the idea of using the non-associativity is extremely interesting, but in that respect, there is actually no limit to the number of generations that could exist. I mean, there's no mathematical hint at this point that it should ever stop at 3, right?
No. I mean, this is a part that I'm still working on. But if you look at the sequences, you find there are limits. And in fact, you can only go up to 7 before it starts repeating. Yes, so there are limits.
So despite the non-associativity, it folds in on itself.
Yes.
Yeah, D. I have switched on.
Yes, Anthony, I know you've been thinking for a number of years on this matter of how to represent SU3 in space-time algebra, and I'm very happy to see this approach, and I think that that's valuable. There is still the loose end of the chirality that you mentioned before, and I'd like to suggest that you consider switching the space-time algebra from a G13 to a G31. According to those are not isomorphic spaces, and I think that there's some possibility that might help.
For reasons I didn't understand, in America, I think one of them is called the East Coast metric, the other is the West Coast metric. And I think there must be a very profound distinction between them. But I don't personally believe that if you're just working with 4D, that there can ultimately be a difference between 1.3 and 3.1?
Well, the two algebras are not isomorphic, and I think if you look at it, there's only one copy of SU2
in G13, but there are indeed 2 subgroups in G31 that are SU2. So you can do an SU2 left and right.
Okay. I find myself a bit surprised still that someone like me who's working just in the 4D, that can make that much difference, but I'm very happy to look at that.
Are there any questions from the chat?
Can I give a comment?
Oh yeah, go ahead.
Professor Lasenby, thank you very much for your talk and for the first part of this talk. especially. From my point of view, you obtain very interesting generalization to the non-orthogonal case, yes, to non-orthonormal frames, yes, and really, from my point of view, you use really nice structures in geometric algebra formalism. So I like it very much. So I think I needed time to understand all the details and the connections between our two approaches, and of course, it will be very interesting for me to discuss the details later, maybe, and maybe it will be interesting for me to read your paper if it is available. Yes, thank you.
Okay, thanks very much for those comments. I mean, your work was certainly the inspiration for this, and I'm very grateful for what you did on this. The paper should be ready soon, and of course we'll discuss with you as soon as we have a draft some of these details.
Thank you, Dimitri.
Thank you.
Eduardo.
Yes. Thank you very much.
I also have a question or a comment.
Let's do this with the online people, and then at the 1:15 we have to go to Chris.
Okay, it's just a short comment, but what I observed and used in the algebra with signature 3,1 is the following: that the set of blades, vector for time that squares to -1, the trivector of space that also squares to -1, and the hypervolume 4 vector also squares to -1, they 3 intercommute and together form a quaternionic subalgebra, and that I could use to construct a Fourier transform for a space-time. And I couldn't do it in the algebra with the opposite signature. So that's just an observation from my side.
Okay. I should mention that some years ago, we had a colleague, Phil Pezalia, who spent a lot of time looking at exactly this question, I think, and he believed strongly there was a big difference between the two spaces, particularly in application to things like gravity. So yeah, very happy to look at this.
Eduardo.
Yes. Yes, enlightening lecture as usual. Thank you very much. So I learned and put things together again. We have a double, dual, and complex quaternions. And in this case, I was surprised that you, because people was rejecting the use of octonions, then you came back and used it. So, and what I learned from this lecture is that when you are using the dual, you get the point at infinity invariant, whereas here you get the current, the current invariant, the J, which is very interesting, right? The
octonions lead to J dot gamma invariant.
Yeah,
that's the norm.
Yes, I mean, and this is something really good news. And also to appreciate the use of the octonions.
Because many years
in the conference, people say, sorry, octonions, Cayley algebra doesn't fit here. So now you say, let us explain how it fits for space and time, and that's something very, very good.
Yeah. Well, and I was actually amazed when I found out that the norm was the time part of the direct current, because that fits in so well with
yes, that's right. Okay.
Remember, you heard it here first. I think this is a memorable moment. Okay, we're going to try and get Chris